This is our first video for Chapter 9. We're going to learn about normal subgroups. What does it mean to be a normal subgroup? A subgroup H of a group G is called a normal subgroup of G if the left and right cosets are equal to one another. So note that we are not saying that AH has to equal HA for all A and G. We're saying that the left cosets must equal the right cosets for all A and G. Note the way that we denote this. This means H is a normal subgroup of G, so essentially it's like saying it's a subgroup, but closing it off means it's a normal subgroup. So let's look at a couple of examples. For our first, I'm going back to our example where we first learned about cosets, where we had H was 111 in the group U30. We found that the left cosets were H7, the right cosets were H7, H13, and H19. What you'll notice is if I were to take 7H, I would still get 717. And we'll learn later that that's because this is abelian. But again, let's just test it out for 7H. So if I'm taking 7H, that means take 7 times 1 and 7 times 11. Well, 7 times 1 is 7, and 7 times 11 is 77, which mod 30 is 17. So notice that 7H is the same as H7, because to find H7, of course, we took 1 times 7, which was 7, and 11 times 7, which was 17. I guess I should be using proper notation there, mod 30. So we can see that H is a normal subgroup. However, here is a non-example. So here we are in D4. Again, that is the set of symmetries under a square, rotational and reflection symmetries. And we can see that H is the same whether it's right or left, because obviously HE and EH are going to give me the same thing. However, HR, again where H is E and RF, HR gives me R and then R squared F, whereas RH gives me R and F. So those two are not equal. Now you can see that H and R squared is the same as R squared H, but HR cubed is not the same as R cubed H. So H is not a normal subgroup. What you'll notice, and we'll talk about these properties later, is that both E and R squared are actually the center of our group, and that is why those end up with the same left and right cosets. Before we talk about how to prove a subgroup is a normal subgroup, I do want to look at an example where it's not true that AH is equal to HA. So AH is not going to be equal to HA for all A and G, but that the left and right cosets will be equal. So it's very important you understand the difference between these two statements. This is saying A times H is not going to be equal to H times A for all A and G, but that their left and right cosets are going to be the same for all A and G. So while it's always going to be true that if G is abelian, and by abelian I'm saying that AH equals HA, if this is true, then we're always going to have a normal subgroup, but it's possible that AH is not equal to HA, and here's an example of that fact. So we're back in D4. Notice H this time is E, R squared, RF, and R cubed F. So if I'm looking at the right cosets, the first coset is H, which is just the original set, H. The second is essentially applying R on the right to each of those. So this was E times R. This was R squared times R. This was RF times R, and this was R cubed F times R. Now again, to find each of those, we start with the value on the right-hand side. So this would be r and then e, which gives me r. This would be r and then r squared, which gives me r cubed. This would be r and then rf, which gives me, as we can see, r and then rf gives me r squared f. And the last one is r and then r cubed f. So it's r and then r cubed f gives me f. Now, for the left coset, I'm applying r on the left side. So this first value is r times e, and then r times r squared, and then r times rf, and then r times r cubed f. Now what we find is that the first value is still r, and the second value is still r cubed. However, when I took rf times r, I ended up with r squared f. But if I take r times rf, remember that tells me that starting at the identity, I'm going to apply rf first and then r. Notice that that value is f. So here I have f, but here I have r squared f. Now those are not the same. However, when I look at the next elements, r cubed f times r and r times r cubed f, again, those elements are not the same, but if you'll notice, those cosets are the same. So we can see that even though that rf was not equal to rfr, we still have that hr is equal to rh, or the left and right cosets are equal to one another, and therefore h is a normal subgroup. Of course, we're now interested in learning how to prove that a subgroup is a normal subgroup. Now, we've already learned the definition that says if you can show that AH is equal to HA, then your subgroup is a normal subgroup. So how do we show that two sets are equal? Well, one way that we've discovered throughout our study in discrete math was that if you can show that each set is a subset of the other, then you've shown that two sets are equal to one another. And that's certainly a strategy that we could use here, but it actually is a harder method than using the normal subgroup test. So that is the way that we are going to learn. We're going to take a look at the normal subgroup test, and in a moment we'll explain why the normal subgroup test works. But let's just take a look at what the subgroup test is telling us. It says if you have a subgroup of H in G, it is considered normal in G if and only if X inverse is an element, is a subset of H for all X in G. So before we look at our two examples that we looked at before, let's talk a little bit about what this means. First of all, this is called the conjugate. It's the conjugate, and it is when you take an element multiplied by both a different element and its inverse, so notice X and X inverse, that's always going to be called the conjugate. Now, what's going to happen is this is going to give us a set of values. So we're going to take each X times every element of H times that inverse of X. And that's going to give me a set of values. And if that set of values is in fact a subset of H, proper or otherwise, for all of the X's in G, then it's a normal subgroup. So it makes much more sense when we take a look at an example. So let's look back at our first example, and if you'll recall, we had H was 1 and 11. Our group was U30. And what I've done here is I've looked at all of the elements of U30 and determined their inverses. So for instance, the inverse of 1 is 1, because if I take 1 times 1, I get 1, which is 1 mod 30. And that's what we're looking for, is 1 mod 30. That's the identity. Now, if I take 7 times 7, I get 49, which obviously is not 1. So the inverse of 7 is actually 13. And again, that means if I take 7 times 13, that gives me 91, but 91 is congruent to 1 mod 30. So that's how I know those two values are inverses. So I continued that process to find that 11 was its own inverse, 17 and 23 were inverses, 19 and 29 were both their own inverses. Now what I've done is for each of those values, I've taken them both times 1 and times 11. So I've conjugated them with 1 and with 11. And those were both from H. If you'll notice what the result is, 1 times 1 times 1, 7 times 1 times 13, etc., etc., all of those give me the value of 1. And if I took each of those times 11 in the middle, or conjugated with them with 11, all of those values were 11. So what is the set of values that I got when I did the conjugation? I got the set of 1 and 11. And that is a subset of H because H was obviously 1 and 11. Now, if you'll recall, the other example we determined was not a normal subgroup. So let's take a look at how that looks. Again, I've looked at each element and its inverse. So E is its own inverse, R and R cubed, R squared and R squared, F and F, RF and RF, R squared F with R squared F, and R cubed F with R cubed F. So really everything is its own inverse except for R and R cubed. So if I conjugate those with H, and if you'll recall, H was E and RF. So here I've conjugated them with E and here with RF. And if you'll notice, I do get E for all of the values here. But on the right side, I get RF, which is okay, but I also get R cubed F. And I get R cubed F 3 separate times. So if I'm looking at the set of values, the set of values is E, RF, and R cubed F. But if you'll notice, that is not a subset of H because R cubed F does not occur in H. Therefore, H is not a normal subgroup of G. I try not to get too proofy in these examples that we go through together and in explaining the concepts. And there is a proof for the normal subgroup test in your textbook. And so I will let you take a look at that on page 175. However, I did want to talk about why it works. So we know that H is a subgroup. And in order for it to be a normal subgroup, it has to be closed under the group operation. And so the group operation is called conjugation, or the conjugate. But I wanted to kind of show you how that worked. So if XH and YH are two cosets, then if I compose them, I should end up with XYH according to the group operation. So how does that happen? Well, by doing a little bit of math, we're going to take XH1 and YH2, where obviously this is some element in XH, and this is some element in YH, which are two cosets, that I should end up with XYH. So if I multiply them, I should get XYH3, where H3 is just some other value. Now, if I take this expression, and on each side, I multiply by X inverse on the left, you'll notice the X inverse on the left will cancel, and on the right will cancel. And then if I multiply it by Y inverse on the left, then Y inverse is going to stay on the left, but on the right, Y inverse will cancel. And then if I multiply by the inverse of the constant in H2, so H2 inverse, that's going to get rid of H2 on the left, and it's going to give me some value on the right. Well, what I know is that H3 times H2 inverse has to be in H, and I know that because H is already a subgroup, and so it has all of the properties of a subgroup. Therefore, if Y times H1, Y inverse times H1 times Y is in H, then I know that that's true. And I could do that the same thing to show that Y, H1, Y inverse. So that is why it works. It's because it's now showing the group operation of conjugation. Here are some properties that we should be aware of with regards to normal subgroups. So if G is abelian and H is a subgroup of G, then H is a normal subgroup of G. In the same way, the center of a group is always normal. The reason for both of these is that for each element, AH is going to equal HA, and again, that's for all A in G. Therefore, it's always going to be true that AH, or the left coset, is equal to the right coset. Again, if that is going to be true if it's abelian, and that's going to be true if it's an element of the center, and the center is any of the elements that commute. Trivially, the subset that includes only the identity is going to be a normal subgroup, and of course the group itself will be a normal subgroup. The rest of these I'm going to have you kind of think through on your own. So for instance, AN is a normal subgroup of SN. So this is the even permutation group, and this is the set of all permutations on n elements. If G is a group and H is a subgroup of G with an index of 2, then H is a normal subgroup of G. We actually did an example like this when we looked at our second D4 example, where we had four elements in H, not the one where we had 2 elements in H. So again, the index just indicates how many left or right cosets there are. And that one should be pretty easy to prove, because obviously if I have 2 subsets, one of the subsets is going to be H, and the other is going to be some element times H, and whether that occurs on the right or the left, it shouldn't matter. Those should end up being the same. Every subgroup of D sub n consisting solely of rotations is a normal subgroup. Again, that one should be pretty easy to work through on your own. And the subgroups, all subgroups of cyclic groups are normal, and that is because they are abelian. Here are 2 practice for you to try. Feel free to press pause and try them both before I go through them with you. So for our first question, we have H is equal to 1 and 1, 2, and we're asking if that's normal in S3. So if you'll recall, S3 has 3 factorial elements, which is 6 elements. Those elements would be the identity. They would be 1, 2, 1, 3, and 2, 3. And they would be 1, 2, 3, and 1, 3, 2. Again, these are all of the permutations of 3 elements. That's what S3 means. So we're asking if this is a normal subgroup. And how do I know? Well, in a normal subgroup, X, H, X inverse, all of those elements are a subset of H. Therefore, each of those elements has to be an element in H. So let's choose any value, any X value in G. So I'm going to choose 1, 3. You can choose any one that you want. So what that's saying is 1, 3 times 1 times the inverse of 1, 3. Well, what's the inverse of 1, 3? It's a transposition, so it's its own inverse. Then that has to be an H, and 1, 3, 1, 2, 1, 3 has to be an H. Well, what happens when I take 1, 3, 1, 1, 3? So 1 goes to 3, 3 stays fixed, 3 goes back to 1. And then 2 obviously doesn't do anything here. And then 3 goes to 1, 1 goes to itself, 1 goes to 3. So that's the identity. So yes, that's an element of H. What about 1, 3, 1, 2, 1, 3? Well, 1 goes to 3, 3 stays fixed, 3 goes back to 1. 2 stays fixed, 2 goes to 1, 1 goes to 3. 3 goes to 1, 1 goes to 2, 2 stays fixed. So that ends up with 2, 3. Is 2, 3 in H? No, it is not. Since 2, 3 is not in H, this is not true. It's not true that X, H, X inverse is a subset of H, because 2, 3 is not in H. Therefore, H is not a normal subgroup of G or S3. Looking at the other example, I have SL2R is that a normal subgroup of GL2R. So if you'll recall, this is the 2 by 2 matrices where the determinant is equal to 1, and this is just the 2 by 2 matrices. So is it true that this is going to be a normal subgroup? How do I know? Well, let's let X be some element in the general linear group, GL2R, and H be some element in SL2R. Note that the determinant of XH inverse by the properties of determinants would be the determinant of X times the determinant of H times the determinant of X inverse. Well, what does that equal? Well, I know that the determinant of H is equal to 1 because that's what the definition of the special linear group is. So this is 1. So the determinant of X and the determinant of X inverse, what relationship do I know there? Well, determinant of X inverse would be 1 over the determinant of X. So if I take the determinant of X times 1 over the determinant of X, I get 1. And because that's 1, then XH inverse must be in H, and therefore XH inverse is a subset of H. So H is a normal subgroup of G. All the work that we have done in this video was essentially for our next video, which is going to teach us all about factor groups.